Hello, my name is Walter Rustler and I'm Director of Sales and Customer Support at Dlubal Software. Today we will present another Dlubal webinar, and this time we handle RFEM and BIM integration with Tekla Structures. We will see the covered scenarios of data exchange between Dlubal Software and Tekla Structures, and we will do also a live demo on a sample model and explain the workflow. We will also see which update options we have when working together with Tekla Structures. Besides the direct link from Dlubal to Tekla, we have a variety of other interfaces that are based on files, like the IFC interface, the DSDB interface, SDNF, DXF, and other file types. However, the direct integration between Dlubal and Tekla Structures uses a direct connection between the objects inside Dlubal and Tekla Structures, and it uses the existing API, the application programming interface of both programs. So we are not limited to the generic definitions of a file-based interface, and we can pick and read and write all the properties of each object inside both applications, as long as they are supported by this API that both programs have. So in a sense, it gives us more specific options to import and export data and to directly connect the objects in both applications. It is a bidirectional interface with update options, and it works in a 32-bit and a 64-bit environment. We can distinguish between a physical model and an analytical model, and it is important to know the difference. In general, when you work in a architectural program or a CAD application, you basically model the structure as you would build it then later. When you do an analysis, you make a more simplified model that doesn't include all objects, like, for example, door frames, window frames, and other non-load carrying parts in that model. Therefore, we have to make a difference between the physical and the analytical model. And in general, there are some problems when you work with a physical model in a structural analysis program, because, for example, a beam might be cut off at the edge of a column, and therefore there is a gap between the center line of the column and the end of the beam. So in the analytical model, we have to overcome this gap and provide a connection, basically bring together all load-carrying parts in one structural wireframe model. And it's a mechanical correct model that includes also maybe 1D members like columns, beams, or bracings. It may include walls, slabs, or other surfaces. And when we exchange data from one system to the other, we have to deal with conversion of different section names, material names, and what we might use in the bill of material in the BIM software or in the CAD software might not be the correct code designation of a material or cross-section in the analytical model. The interface between Dlubal and Tekla takes care of this conversion, and the analytical model is inside the Tekla structure model, and it is derived in some way automatically from this architectural or physical model. We'll see this live later. Additionally, to this, to solving of the over transition from the physical to the analytical model, we also can handle or include support and release information inside the Tekla model, and load cases or load combinations, as well as standard loads inside Tekla. Those are the most important objects that Dlubal software can retrieve from Tekla models. When we import a model from Tekla Structures, we can choose between the physical and the analytical model. And I explained it a little bit before, but here are some more pictures that maybe give you a more clear picture. And we see here, for example, in the bottom picture, there is an analytical model with a yellow and red bars that are shown. We have releases shown in the represented like circles. We have analytical nodes where both elements connect. In the physical model, we only see what we actually would see. We see the real model, actually how we build it. And inside Tekla we have access to information like how is a beam connected to a column? Is it a moment connection, or is it a pinned connection? And I can set the degrees of freedom. Typically this information in a architectural software is of no relevance. And in normal cases we will retrieve this analytical model from Tekla Structures, and if it's set up correctly, we do not have to have a lot of work inside our software. We can get basically the ready model for analysis directly from Tekla Structures. Additionally, we can import load cases and loads, and the basic loads I would say. We can also import rigid links that may be created by Tekla when center lines do not match. We'll see this later. And I have special features that we implemented for some specific customers that would like to have for each member in Tekla a additional single cross-section definition inside Dlubal software. So if you have 1,000 members, you get 1,000 different cross-sections, for example, inside Dlubal software. However, sometimes I think it's good to merge all those cross-sections. If we have, for example, 10 columns, they use all the same cross-section and they are fabricated in the same way, then we have to have maybe only one cross-section representation inside Dlubal software that has some advantages in handling. Another typical problem is when you exchange data from one program to the other is the direction of the global axis, the global z-axis. Once it goes up, it may be changed to downward in the analytical application, or vice versa. So we can mirror this information automatically. When we export to Tekla from a either new model or from an existing model that we imported earlier from Tekla, we have additional options. For example, we can override the existing structure. That means we erase everything which is in the current Tekla model and we create our new model that we have from Dlubal software. Or we can append to an existing Tekla structure model. For example, if you have one part already done in Tekla and you want to get another part of a building added to this already finished model in Tekla, you can compose a larger, bigger model from several individual models from Dlubal software. For example, you can analyze frame by frame and then individually update your Tekla model with each new frame. Or you can have one building and add another building if you work in a 3D environment in the Tekla model at the same time. The most interesting but also the most difficult part is the update existing structure feature. This will merge a changed Dlubal model with an existing Tekla model. So the typical workflow is that you retrieve a more or less prepared analytical model from Tekla. You do your structural design inside Dlubal, RFEM for example, and then you export the changes and you update the existing Tekla structure model. When we do this, we have different update options that I will also explain in another slide. Options we have here is to create what we call set of member. For example, imagine you have a long main girder in your structure and it's one part in Tekla Structures. On this main girder you have additional cross beams that connect somewhere along this main girder as secondary girders. And when I analyze it inside Dlubal software or typical all other software, then you have to make a connecting node where those intersection points are. So inside you have actually 3 analytical members maybe where there is only one major part in Tekla structure. We keep this information by means of so-called set of members where we can combine several linear connecting members to one major big member. And we refer our data exchange to this, what you might also call physical members inside Tekla structures. So when I update the model, I get one big girder as I would like to have it in Tekla structures instead of 3 individual members. We will see this also later. I can also update the Tekla model with additional information like internal forces, and these internal forces can then be used inside Tekla structures to have a better idea of what type of connection and which type of bolts and thickness of plates I might have to use. So Tekla inside has the option to display internal forces, and we can fill these fields with the correct values from the calculation. Updating allows us to update coordinates, materials, profiles or cross sections and thicknesses of slabs, walls. I have also here another special option that is called remove non-existing objects. If it is checked and I export into an existing model and I have in Tekla something which is not there in the RFEM model, it will remove this non-existing object, this in RFEM existing object also in Tekla. If I leave it unchecked, it leaves everything untouched in Tekla what is not there in RFEM. Maybe it is a little bit complicated to explain by words, but it has a meaning. Okay. Additionally, we transfer information like the node numbering of the Dlubal analytical nodes or the material or set of member numbering. So you can find the parts that you see in RFEM also in Tekla structures. By inquiring the objects, you will find there, okay, member number 235 in Dlubal, this is what I have here now. And I can go to the Dlubal model and see, okay, where is member number 235? All those user attributes can also be displayed on a drawing, for example. So it would be a good way to use it for a overview plan that displays the numbering of the structural objects maybe, or whatever you need it for. Anyway, we can update the Tekla model with grid lines, with information about the used materials, and also the node numbering, and additionally comments. That means I can write there, for example, this is a new beam, and then this comment will be also there as a user-defined attribute, which you can use then for filtering inside Tekla and so on. The typical covered scenarios are a round trip that I explained a little bit so far already. There is the Tekla model that includes the analytical representation of the model. We do the design inside RFEM and we update the Tekla model. So it's linearly displayed, but basically it's a circle. So this is one process. We can add, for example, in the interface during the work inside Dlubal, we can add bracings, we can add openings, we can remove or change columns, we can change cross sections, and we can do those updates. Another option would be, and we will see this live in a few seconds. Another option is to start modeling inside RFEM. RFEM has great modeling capabilities as well, and or you can retrieve a model from somewhere else, from other applications, and we do the structural analysis, but there is no Tekla model. But somebody would like to have a Tekla model from what he has created inside RFEM. So we can just export it and create also a Tekla structures model from scratch. The advantage of this is that you can, for example, you are a draftsman or a detailer, and you need to know which cross-section is used for which column, for which beam, and maybe if there's a simple model you understand and you can read it, but if there are, imagine there are 1,000 members and 500 different cross-sections, then it's not so easy to even know which cross-section is where. And if I have a Tekla model and I'm a Tekla detailer, I might want to work inside Tekla, not so much inside the RFEM viewer. So I can use my environment, my well-known tool, to get this information and to communicate it with somebody else, or to use it for even detailing and modeling. All in all, it is all about saving time, increasing quality and productivity, and this at the same time means also avoiding errors, and you have, I think, very well matching tools here with RFEM and Tekla structures. Before we go to the live demo, for those of you who are new, you can show and hide the control panel that you see on your screen with this red arrow. And you have a question panel, and there you can type in short questions that my colleague, Robert Vogel, will help me to answer. He's joined us today, and thanks to Robert, he will be available for you to answer your brief questions. Please keep the questions simple so we can quickly answer them. If you have more difficult or wider questions or deeper questions or other questions that maybe have not to do with the webinar today, do not hesitate to contact us, sending us an email at info@dlubal.com or hotline@dlubal.com, and we will get back to you as soon as we can do it. The next will be the live demonstration. We will do this 3D building here and import it from Tekla Structures. But before we do this major structure, I'd like to explain a little bit the options you have inside Tekla. I would like to point out that I'm not a Tekla expert, but I can show it a little bit. And if you have questions to Tekla, please also contact your Tekla vendor, your Tekla company. You can find at tekla.com. I'm sure they can help you out in more detail. I have Tekla open in the background, and I'm now inside Tekla Structures, and here I have a simple model which is not very spectacular, but it includes a few things I think that are important to explain the use of this interface. So here you see the physical representation of this model, and you see here there are certain beams and columns. We have here the situation that some beams are top of steel, some are maybe connected center line, above, whatever. We also have here a column that is, there's a typical situation where there's a wide column and a narrow column, and then how to model this in the structural design. The special thing about Tekla is that it has a analysis and design option here. And I start this, and I have prepared already a few models, and I can, for example, show when I select this model what happens here. I get a display of the actual analytical beams, and we see here, for example, here now everything is modeled by the center lines of the columns. So the statical model is in the center line of the physical model, and because of this we have here a offset, and this offset is closed by a rigid link, which is shown there in blue. This is done automatically by Tekla, more or less. Then we have here the beam on top of the frame here, and here the analytical line is in the center line of the top flange. So it is important because you might want to have the correct column length or the maximum column length, and if I analyze it in the center of the beam here, then I would lose maybe half of the depth of the beam and so on. And maybe if I have a wind load there, wind load is not big enough. Huh? So how can I do this? I create something like this new, and I say here create new model. I can have several models inside Tekla, inside one Tekla model, and I can say this is my model new 2 maybe, and here I can select whether I want to use the full model or only selected parts or different settings. I can apply filter if I want to. I can also auto-detect secondary members. There are various options inside Tekla that we even don't use. Tekla is a very well-known, widely spread software that connects to different applications, and some of the tables here or the registers here are not used by us. We use basically what I'm showing you now. And here we have a Dlubal.net plugin, which is installed when you installed automatically when you install Dlubal after Tekla is installed. So during the installation process, Dlubal looks for Tekla structures. If it finds it, it will automatically install this plugin. And then you can select this interface. There might be other interfaces here listed in Tekla to use. And then we have here more settings. And in those settings, we can set up the reference axis, member axis location. And this is an important thing. Now it's set up reference axis eccentricity by neutral axis. I can also use, for example, the neutral axis. If I do this and click OK, you see what happens. All the the analytical members are moved to the center of the physical member, yeah? Because we have here a different depth of the sections. We have the problem that the center lines do not meet in one point, and Tekla automatically creates here so-called rigid links. Also inside Tekla we have here, for example, support conditions symbolized by a white block here. If I edit the member here, okay, let me see, to edit it, okay, it's possible typically to, maybe I have a filter which is not, yeah, I show this later to you. We see here that there are numbers for beams and for nodes. We see here the supports. We see here how the physical model changes. Yeah? If I change it again, for example, to not neutral axis, but reference axis. If I do this, it is rebuilt automatically, and you see here other placement of the center lines. Okay. Yeah, I didn't activate my mouse arrow here. So let's say I want to change something here, not globally but locally. For example, here I would like to say this analytical object here should not be on the reference line. I can change it, and I can say here, okay, position, not reference axis, but maybe neutral axis. And I modify it, and axis, reference axis, let's see what happens. I had this problem also yesterday during a demo, and then it worked, but never mind. You can do it also individually. That means you can do it globally, so all the offsets are changed, or you can do it member by member. Let's take a look at the support conditions. If I click on the column, for example, you see here start release is a support, or it can be a pinned support, or it can be only connected, or you can have also free definitions. Then you can enter here some spring constants and so on. Or the end release is only connected. So on the top here we have no connections. Or the same thing here for the beam. I click on it and I say start release is connected. We see here with a release, and I see here a circle. If I do not want to have the release and say I want to have it fixed, I modify it, and then it's changed. So it is possible to individually adjust this analytical model. I open another model here. We see, for example, there are also loads. I can display the loads basically here. You see here there's a load inside Tekla Structures where we can apply the magnitude of the load, and this is also possible to implement inside Tekla. Okay, maybe I try to import this model quickly into RFEM. I open RFEM here. In RFEM, I open the direct import from Tekla Structures, and I get my import option that we just saw in the slide. I want to import the analytical model. I import load cases, the rigid links we see, click on OK, and now I have a selection of the various analytical models I have inside Tekla Structure. So the same models that I have here are given to me as a choice inside the interface. So now I use the model with the load, which I'm just displaying here. I click OK, and there is a little bit of a protocol that goes through, and then I have here my structure inside RFEM. We also see there is a the load is here. And if I go to the wireframe display, we see here also we have rigid links, we have the offsets that come from the Tekla structure model. We see here also the support conditions are here that we can use and so on, and also the columns are have this offset here. So this is how you can set up your model inside Tekla Structures and change it and already prepare the structural model inside Tekla Structures. Now I'll use the more complex model that I have prepared, and I open this inside Tekla Structures. This model includes not only beams but also slabs and walls, including openings, and I prepared several models inside already. You see here it's a hall including a second level here, and there is a basement including some slabs here with openings, windows, and so on. Inside this model I have prepared already the analytical design model. Actually I've prepared several models. I have prepared, for example, the concrete part. So I only get the concrete part here. For example, I can quickly import it here. Concrete, and import here the analytical model. Okay, I don't want to load this time, and say here concrete part. So even though I have a 3D model in Tekla Structures, I can load only part of this model, and I can say, okay, now I don't want even the 3D concrete model. I want to have the maybe only one floor or one slab in the first level. So I have just one slab here that I can work with. So I can do a simplified analysis. And also the same way I can say I want to have only one end wall, and I do like a 2D analysis of this end wall here, for example. If you want to, you can import only one beam if you want to. Please note, here's two analytical members. Inside Tekla we have one part. When I update it later, it will be staying one part inside Tekla. Okay, but actually I want to have the entire model. Maybe I explain a little bit about the entire model that I have done in Tekla Structures. Here we have support conditions, which are pin support. We have here set up releases already at the ending of some beams here. We have openings. I've made the model in such a way, for example, that those beams here are modeled as top of steel, and this analytical model lies on top of the in the center of the top flange. So it's one level. And important is when we update the sections later, that those sections, even if they change in the section, they should stay top of steel. Okay, also here the walls are modeled as center lines, and the slabs as well. So I'm closing the model here and stay with the physical model view, and I start inside RFEM and I import the analytical model, including rigid links, which I don't have at the moment, and I click OK. So now I choose the entire model, click OK, and we are importing the entire structure. We see here we have the supports, we have a variety of releases here, We have the openings. We have also, we see it on the display that we have already cross sections imported, and when I look at the table of cross sections, I see here they are all converted from the Tekla designation, which is here, which is missing the blank between the IPE and 550, but Dlubal has a blank in there. So we internally map all these cross sections. Also, the materials are already set up according to Eurocode, and in Tekla the material name is much more simple. We include the code. How does this happen? When we import, we have a variety of files, of course. We use direct import from Tekla Structures, and in the details settings, I have the option to set up a conversion file, or I can edit this conversion file. And here, I set up which name of the material or cross-section should be converted to which name inside Dlubal's software. So I have the option to import, export it from Excel, and I can set it up in my company as I like it for my typical materials I use. And once I have adjusted it, it will be valid all the time. The same is for example, for cross sections. You can use this very well if you have non-standard sections that are coming from different vendors. Everybody has his own designation, and for us it is basically impossible to know all the names that are existing in the world. So therefore we match the Tekla name and the Dlubal name, and remember or can now translate those cross sections automatically. Okay. Now we'll do a brief structural analysis with this model here, a 3D analysis. We'll change some cross sections, we'll add some members, we'll do some concrete design. It's a totally, basically independent model from Tekla. I can do whatever I want with it. It's not somehow special model that only can be used in conjunction with Tekla. So it's totally independent. First of all, I would like to know if it's really working, if it's really well connected and done correctly. So I do a first run and do a brief analysis. First of all, I need a support on this foundation slab here, and I enter this support inside RFEM. I select a non-movable support as a first idea of this support condition, and edit the surface and add it there automatically. Next, I need a load case to see how the deformations are, or if it calculates and if some parts are loose. So I do this simply by creating a new load case. It's called maybe self-weight of the structure. It will be done according first order with a default mesh of 50 centimeters for the slabs, and we'll do a analysis. And it seems to be working. I have here now a moment diagram which looks reasonable. I have here maybe internal forces of the slabs which look pretty okay. I can maybe show also the deflection, maybe not now for the concrete, which is rather massive, it is almost zero, but maybe I only show the steel parts, concrete surfaces by concrete, but members by material. So we can see here all the deformation lines of the members. I can animate them, and this way I can find if there are some loose parts usually, and it looks all good. Also, the support condition should be more or less symmetric, which is here at the columns, at the corner columns, and there's a little bit of difference because here we have this floor structure in here, but it looks quite okay. So my model is of good quality, and I can continue doing the design process. First of all, I have to create, maybe I've checked another thing from the structural point of view. I need some bracings here in the roof. Typically, we have some bracings here. The first level here of the grid is supported horizontally by the concrete part here, but the roof structure maybe is a little bit unstable, and I would like to have a bracing here. Before I do this, maybe I prepare some typical views of the structure, and I select the roof, and I create a new visibility from this roof structure like this, and I say, okay, this is what I like to save, and I create a new user-defined view. I call it roof. Next, I would like to do similar things, for example, with the floor here and the additional slab here. Maybe I can select it also like this, and I say, okay, show me only the selected parts. This is another view I'd like to save, and I say floors. Additionally, when I go to the default RFEM view, it's displayed this way, but Tekla always uses this kind of view. If I go back to Tekla, this is their default view. So in order to avoid confusion, I'd like to save this view as well, and I write there as Tekla. From now on, if I need a different selection of my model, I click on here and I have everything I want. Okay, let's start with the loading. When I go to the general data of the model, I can set up to do the load cases and combinations according to a certain code. I'll use Eurocode for this. I have here the various national annexes. Because we have international audience today, I use the general Eurocode settings, which are available at the detail settings, and we have here access to partial safety factors, combination factors, consequent classes. Once I do this, I can also create combinations automatically. We stay with a 3D model. The advantage from now on is all the loads I enter and all the load cases I entered are classified according to this code for snow, wind, and so on, and the software knows automatically which combinations to create and which combination factors to use. I can do it most comfortable in the tables, which I can display or hide, and there is next to the model data, there is the load cases and combination data. As you've seen or heard also, there is done an automatic combination, but as soon as I change the load case setting, and it doesn't regularly sense to have combinations with just one load case, it will update or delete these combinations that have been done automatically before. I create next to the self-weight a second load case called snow, and I have access to all the categories, action categories for Eurocode. I have wind as a next load case and another load case. It's not here, I type it here, live load. And then, because it could be anything written there, I have to make sure I choose the right category, and this should be an imposed category B on office areas. Okay, I have 4 load cases, which should be enough for this demo. I have actions, which is a first summary of all the wind load cases, all the snow load cases. They are summed up in actions, and then we combine the actions. Typically we have an ultimate limit state combination and a characteristic or frequent or quasi-permanent combination. I want to do a preliminary design, so I'm only interested in the design ultimate limit state combination. Then I do a combination based on the actions, and I do a combination, the final combinations basically, which include the load cases and the safety factors. So now I see load case 1, 1.35. Most likely this will be not controlling. Or I have load case 1.5, load case 3 1.5, which is load case 3 is, I think it was wind. I leave it out because I have load case 3 somewhere with 1.5 in another combination. So you don't have to, you can calculate everything, but you have a selection here what you really want to calculate. So you do not turn off your brain. You control the software, not the software is controlling you, and you also see exactly what the software does actually. Okay, then from this 13 or whatever combinations, I can have a result combination, which is the envelope of all the calculated combinations before. So I get a max-min summary of all the combinations I have to analyze. Okay, this is the combination part. Now we talk about the actual loads. Self-weight is already here, and as a self-weight of the structure, but I need to add now the actual loads. So I go here to the wireframe view, and I add now a roof load quickly. It's a surface load to load case 1, and the magnitude is in this case 0.5 kilonewton per square meter, and it should be global direction, but related to the true area. So I pick my boundary nodes of the surface, and I can continue doing things for multiple surfaces. On OK, I return to the dialog, and I can select parallel members that should not be loaded. So only the red members will now be loaded. I click OK and OK again, and I get some summary and some statistics, and I see here my first area load. The next load, our self-weight load, will also have to be on the floors. That's why I prepared this view. And I create another area load, a little bit more on the grid here, and select here the individual corner nodes. OK, OK, and also decide that the distribution of the loading should be on the cross beams. OK, and 2 more surface loads on the slabs, 0.5 here and here. While I'm working with the slabs, I remember I forgot something. Those slabs now are rigidly joined with the walls, but I don't want to have this. Therefore, I double-click the surface. I say here releases, and I add a linear release that sets off all the spring constants for moments on all the edge lines of the surface. OK, OK, and then I get displayed a linear release on the edge of the surface. And the same thing I do here with this second surface, create a new release, also the same type, so there should be no moments at the edge in the wall. And here, because it does this automatically on the opening, I have no wall, so doesn't make sense to have the release there. I can just select it and delete it. Okay, Now I think I have everything regarding the model. We've looked at the self-weight load cases, and we continue with snow. Snow is something for the roof. Okay, quickly have the roof here. And I have a tool called snow load on dual pitch roof. I can use the Eurocode here. And I have again national annexes. The ground snow load should be 1 kilonewton per square meter. And I pick now the boundary of this dual pitch roof. Okay, there are 6 nodes I have to pick. It should go in the load case 2, which is snow. It automatically filters it and remembers it. And then I say again, only on the main beams I want to have this loading. Okay, I get again some summary and my final snow load on there. Next is the wind load. Wind is on the entire structure. And I go to wind here. And I would like to have some wind in -y direction. So I add a wind load as force in global y direction, -0.5. Okay, on this surface and on this surface. On the opposite side, I have a little bit less. I create here again a smaller surface load. 1, 2. I also need some loads for the columns. Member loads, global y direction. It should actually in the projection, if it's not straight, not vertical, -2.4 as a member length, as the member load. 1, 2, 3. On the edge, there should be some lower value, maybe only half. Okay. And then here on the opposite side, again the same thing, but -1.5, a little bit less for the center columns, and -0.75 for the edge columns. Additionally, I have a wind load on the roof, and I use the generate wind load on dual pitch roof function. Again, according to Eurocode code, I need the height of the structure, which I can grab from the structure, and I need to select the roof points. 2, 3. Okay, one more. Wind load. Okay, I have the height. Everything is fine. Now it's important to understand where the wind blows on the structure, and you see here A, B, C, D, and I use this order to select my nodes as well. 1, 2, 3, 4, 5, 6. And the wind load should be analyzed or going to the load case number 3. And I only want it on the main beams as well. You can see in the background also the impact categories or areas, G, F, H, J, I, as in the code. And OK, and it creates my uplifting wind load. Okay, last but least, we have a live load on the floors, which is basically simple. We can create another surface area. It remembers the last input, so I only need to add the actually live load. Okay, and it's updated here in load case 4, and the same live load 3.5 as global C direction on the slabs. Okay, it is more or less complete now. Of course, I understand that wind loading can be much more complex. We need some load maybe that is working off the end walls here and so on. It is, I think, extra work that needs to be done. We have for typical structures, we have wind load generators as we've seen for the roof. But for our demonstration here, it should be enough, and we will do the analysis now of this structure. Maybe before I run the analysis, I remember one more thing I'd like to do. I got a call from the architect, and he says, I want to have the same opening which I have in the first floor, also in the second floor, because otherwise there is no way to get up there. So we need to quickly copy this opening. So I select the opening, I move copy it, make one copy, and I copy it from here to here. Okay, okay. So now there's an opening also on the second level. Okay, now we run the analysis, or we go to the design basically. Design is done by the additional module Steel EC3. I'll briefly go through this module. There are other webinars that already cover this module, as well as there will be another seminar covering the concrete module, which I will show in a few seconds as well. But I will not explain now all details, because we want also then to exchange data with Tekla. Now we go to the RF Steel EC3 module to optimize some of those sections. We have Eurocode design, we have here also national annexes, and I select a series of members I'd like to design. Here I'll use the fuse tool again to select, for example, members by material. So I hide all the concrete stuff which has nothing to do with EC3. Also, I can do similar things like members by cross-section. And if I open here this filter, I can say, please do not show certain members, for example. I don't want to see those. It has a reason, because those main girders I will do in a different design procedure, but those will be all done as members, because all those members have design lengths equals to member lengths, with the exception maybe of the columns, but we'll neglect this in this case. I select for design the ultimate limit state combination that I have pointed out before, and now I'll select also the set of members, and I can now select, for example, clear. I select those main beams that are here, which are 6 main girders. Okay, and the design length of these main girders is the entire length from the wall to the pitch of the roof, and it has a local support which is held by the frame, which I forgot to enter, I see, which is supported by the bracing, which I forgot to enter, in the center. So the buckling length in the weak direction of the cross section is smaller. I can select now in the stability design that I want to use the equivalent member method, or I can use also the general method, but the equivalent member method is maybe more simple in this case, and is the more general option that typically is used, and that's why I selected here. We have the materials, we have the cross sections that are imported now from the structure. We have lateral intermediate supports for members, and we have effective member lengths, and we have effective member lengths for set of members. And here I select the factor 0.5. So about the local axis C, which you can see here, the bending will be, the backlink length will be only half of the actual member length. And with the use of set of members, I can handle this very comfortable. Otherwise, I have the option to take into account rotational restraints from a steel deck, for example, or shear action also from a steel panel, which is, of course, increasing the stability of those beams. Okay. Before I run the analysis, I go back and I will enter the bracing, which I forgot. Let's go back to the roof. I have a tool that quickly allows me to add bracings. Tension only members. I create a new cross section, which I can just enter here. And I can select steel as the material. Now you can go either to the library to pick it, or you can enter it manually. If you know the name, it will automatically read it from the library. Okay, it's tension only members, and now I can just select the bracing crosses here, which the software finds automatically the enclosed cells and gives me a symbol, and I can select those symbols. And otherwise I would have to manually enter all those beams, which is more complicated, and quickly I've created my bracing here. Okay, here we go. We have the entire model, and now maybe we have to talk about concrete as well. Let's design that too as well right away. Concrete surfaces. We go to the surface module, and we also want to design the result combination 1 according to Eurocode with the national annexes for the general settings. I have the materials as well here, the surfaces, and the reinforcement settings. I don't want to investigate all surfaces. I only want to have my 2 slabs. Okay, and here I need to talk about the concrete cover. I want to do it according standard. I just select the exposure class. Now let's stay with XC1, and I get automatically the required concrete cover. I can do a provided reinforcement that I decide to enter there anyway, on top and bottom to avoid cracks. There's also an option to analyze the crack width and so on, but for my preliminary design, I say I want to have this wire fabric here, and I like to check the minimum longitudinal reinforcement and so on. So this is it for my settings, and I think now I can just calculate everything. Calculate all. Now RFEM will calculate all the existing load cases that I have selected for calculation, and I hope everything is going well. I haven't checked it with the real loads, only with the self-weight loads, and it will take now a little bit. It's a nonlinear analysis. I can set up that combinations are done linear or nonlinear. Typically it's linear for load cases and nonlinear second order or P delta for combinations, and we use now a nonlinear analysis, which is taking into account the additional moments from deformations. So equilibrium on deformed structure is maybe the important sentence to say here. Okay, after a little bit we will get hopefully the results. Combination 12, and I think we have 13 all in all. So there are several iterations because we have failing members like the bracings, and also we have the second order iterations anyway. Okay, now we go to the concrete and the steel design, and we get finally some results. Okay, let's take a look at the results maybe for the internal forces. Result combination 1. I go to the wire fabric display and wire display, and we see here bending moments, for example. From ultimate limit state combination, we can set up here axial forces, bending moments, strong axis, weak axis. Looking at the weak axis bending moment, I see here, I don't like to have that. Maybe it's better, maybe there's something wrong with my orientation. Yes, I have a frame here, it's a bending, it's a moment connection here, and it goes into the weak axis of this column, which is not good for design. So probably I have to change this. I remember this and do this then later. Let's see what we get on stresses. Steel EC3, ultimate limit state, design ratio is 2.55. Let's see which cross sections are a problem. I go to the cross section table and see here, okay, there's a problem, not a problem here, not a problem here. These seem to be okay, but these main girders are a problem. Then we have the cross beams here, which are pretty okay. And I'm missing, actually, now here they are. These are the main columns here, which are not so good. We have IPE 400 here, and it's no good. So something needs to be done. Probably it would be a good idea to have here an additional column, and also maybe to support these main girders here. Some design considerations that maybe are done while the structural engineer is doing his job. Also, maybe I'd like to optimize those cross sections, and I optimize them from current row. This means I optimize, I don't change the type of section. I use a AGA, for example, and I stick with an IPE here. And this I want to change anyway, so I leave it. Those main girders maybe can be smaller, so please pick another one. Then we have here the columns here, which I need to change, but anyway, I'd like to set them up for optimization. I also want to optimize those, and my main columns I want to optimize as well. I run the analysis maybe now only in the steel check. So I rerun the analysis here, calculation, and see what I end up with my internal forces that I have now. So it picks a AGA 120 for the corner, 140 here, which sounds reasonable. 500 is okay. We have 240. Okay, let's stick with it. 240 for instead of 330 here, and this is 600, so there's nothing to be done. But now I have like the blue cross sections are optimized, and I can export them now to RFEM to update my internal forces. I do this now because I have a better idea already from these cross sections. Okay, 6 are updated now from the initial design, and now I'm doing my model changes additionally. That means I want to have a column here. I pick the type of column from an existing beam, so I have the orientation and the cross section correctly. Say okay, from here to here, and the same thing from here to here. Also, I'd like to have this little column here at the same type. I copy it, make one copy from here to here, Okay. So everything seems to be reasonable. Now here on the top, I want to have a additional member release. So I have easy connection up here. At the other end, I cannot forget to rotate my columns here by 90 degrees. So they are carrying the moment in the right direction. Voila. With this, I go back and run my analysis of Steel EC3. I just click, please show me results of Steel EC3, and RFEM will automatically update the results. So this takes another few seconds, which allows me to explain something more in the Tekla model. In the Tekla model, I also have here connections already. So the connections may be done now while the structural engineer works on the design. And the connections are here. It's a very powerful feature of Tekla Structures. You see here connections are there. We see here also that these parts are one part, one beam. This is one beam. These columns are one part. So it is a different model. The analytical model is a different model than the structural model. Let's see what RFEM does. So we have a nonlinear analysis here. And okay, I'm thinking I'm running into a slight problem here, which I need to close and see what happens here. Okay. We have combination 11 now that is analyzed. And then we should get some result. Okay. Now we get into the analysis of Steel EC3, and we have a design ratio of 95%. We open the Steel EC3 module, and we see here the utilization ratios are quite okay. We are back to very low utilization of the main beam, EPE 600, which is the column here, which is low. Then we have here 600 here. So we could optimize much more, but we have some changes in the cross sections. Let's have a brief look to the concrete results and do the concrete analysis. And we get here, I can use my view again, floors. Okay, but I need the results here, concrete. We see here top reinforcement in one direction, in the other direction. We see here bottom reinforcement in two directions. This is the required reinforcement, and we can here show the additional required reinforcement. So I have a basic reinforcement, and everything which is above this is now shown in different colors. So basically you put your wire fabric in here, and you put in the additional reinforcement here where we have the colored parts. Okay, my design is so far done. I'll keep my results here. Result combination 1. And we can now update the Tekla model. So I go to Tekla Structures. The model is here. I've pointed out the connections. We go to RFEM and we say update existing model. So we update the existing model. We also export the internal forces, and we click OK, and then we go to Tekla Structures and see what happens. After a certain time, we get the updated model. We see here now we have the bracings. We see here now we have the changed cross sections. We have here also the updated internal forces. Now I can do undo, and you see the changes. We have the columns here, redo, and see how the connections follow the changed situation. So also we should have the opening here, and yeah, we can also check if we have internal forces. We see here also this part of the structure is still one part. It's not two parts like in the analytical model. I can right click on it, inquire part, and we see here information from the Dlubal software. We see here the internal forces, bending moment, 188, shear, axial force. We see here also the member number or in the Dlubal software, material, and we can reference to those objects as well. So let's see whether we find it. 167. I go here, member number 167. Yeah, I can select it. I can say, please show me only the selection. Excuse me, show me only the selection. And I want to have the results here of the internal forces, 188.5, and this should be the value here, 188.5, moment M2. So now we can use this for information in a connection design, for example. Okay, this is also important to know that all the beams, for example, still are top of steel. All the work that has been done by the detailer is still not lost. It's updated, and we get here the changed situations of cross sections, surfaces, openings, and so on. This is what I wanted to show you live today inside our software and in Tekla Structures. I hope you could learn something from it and everything was interesting for you. Let me go back to the PowerPoint presentation, and I'd like to point out a few more things for you before we separate today. I think Robert answered quite a few of questions. Maybe I should take a look at those before we do the information with the other software. There was one question whether we can handle general sections or non-standard sections. I have shown you the mapping file. Maybe I need to maybe I need to explain this in a new structure. Hang on, I open a new model. I save it maybe better. Sections, no, not, okay, we can use that as well. This is a typical question, and it's not surprising that it comes up here as well. Here, for example, I have a few non-standard sections. For example, something like a C section, or these are sections with variable depth, parametric sections, and I can also do things like in RFEM. I have also a typical model for it. I can go here in the project manager. Hang on, open it new. And we go here and find sorting models. Just a second. Sections. Maybe now. Okay, where is my model? Okay, never mind. Let's use just a Tekla model. We can do it that way too. I create a new file. Okay. And I import this non-standard section from Tekla, it doesn't matter, we can go this direction, into this file, import, okay, analytical model, okay. And here I have my new cross-sections. For example, there is this C shape, and there is also a boxed shape, which is called in Dlubal, for example, like this. Yeah? But in Tekla, it's called differently. It's called WB 500 and so on. Yeah? But we internally mapped those cross sections, and I can change it now here. For example, I go into the material library and I change it here to, let's say, 900, yeah? And maybe this should be 1000, yeah? So it's wider. Okay, okay. Where I can change also the depth of this welded section, yeah? Where I go in the library. It's better to maybe do this in the tables. Hang on, you can see it better. Cross sections. Yeah, and I change it here to maybe 1200. Width should be 200, and so on. Yeah, I right away have all my cross section data here. Okay, okay. And this changed information I send to Tekla now, and I update the structure. Update existing model. Okay. And I look into Tekla, and everything is updated now. Yeah? I have here 1200, and I have here this parametric section is also updated. One more word to this C section here. In the import detailed settings that I showed you at the beginning, you can see here the mapping file for materials, but also for cross sections. And here I have this cross section here. Yeah? So in Dlubal, this section is called KC200 by 2.5, provided by Starbar, and I map it this way. So in this way I can map any cross section I like, and you can very comfortable work with this import export to Excel options to create such mapping files. Standard cross sections are mapped by default with the software, and others can be handled with the mapping file. Question was if we can import and export IFC files. I can show you this as well. IFC is supported here. Import industry foundation classes, IFC. We support the structural analysis view and the IFC coordination view. It is important to know the difference. The analytical view includes representation of node at beginning and end, and support and releases and loads, while the architectural view, which is mainly used also by Tekla and by other BIM software, they include basically a 3D representation of all, or solid representation of all the parts and objects. So we get a bunch of lines for a cross section, for example, and if you import a slab, you would get like a 3D rectangle which has a thickness and everything, but it's not so good for us to import it from an architectural view. We should have the analytical view. So IFC is not IFC. It depends which object model you use. We use the structural analysis object, and there's not, unfortunately, not so many structural analysis programs who support this. And the coordination view is somewhat compromise. So it's meant to exchange the load-bearing structures from the architectural model, and it's a reduced model from the architectural model, and we import this and we can work with it, but it lacks the information of like loads and supports and releases and so on. So it's possible. There was one question whether we can import-export connections from Tekla. This is not yet done. We're thinking about exporting our connections from our connection modules. It's a matter of matching the components in Tekla as well as what we have. It's easier to draw the connection than it is sometimes to analyze them, but there is something that we consider to do there. Can I use springs as a release in Tekla? As I said, in Tekla, you can set up in the analytical model, excuse me, you need to have an analyst model. You can set up releases here and also spring constants. They can be, for example, a spring. And if you have this spring constant, then we also import this spring constant inside our analytical model. Then there was the question, again, can I export a model from Dlubal to Tekla? Yes. We write always the physical model, so we're not writing the analytical bar model, but we write the physical model. Maybe I can create a new model or open an existing model here where I can empty model that I can use to export something into it. Let's see what I have here. We can, for example, use something like this. This is a real project from a customer of ours who did some analysis of a multi-story building, and we can export this to Tekla Structures, export, update existing or override in this case. Okay, we have no results, so after a while we should see the model showing up here. It's built up here, and we have here the 3D model, and Tekla users can use it and work with it as well. Okay, I think Robert answered most of all the other questions, and also I think we have spent a lot of time. Usually I plan to be here for like a little bit over an hour. It's 1.5 hours. So let me point out a few more sources of information. You're welcome to visit our website, dlubal.com. It's changing constantly and includes more and more information, more up-to-date information. Follow our social media channels. Especially I'd like to point out the Dlubal blog, which is an interesting place where we blog every day with new hints how to work with Dlubal software. It's in different languages, and you can search here as well, and it's a very interested visitors site of ours, so it's a good source of information. Please also inform your colleague about it. It's very interesting what we hear from our customers. Also, I'd like to point out the download page where we offer trial versions. Trial versions are full versions that work for 30 days, and you can also try out the interface to Tekla if you like. After that they turn into a demo version which has more limitations. When you would like to get familiar with the software, use the page Help for Beginners, First Steps, which has information where to find introductory examples and a tutorial how to get started with the software. Also, those webinars, as we do today, are on our website. We can you can look at recorded webinars. All you have to do is you have to sign up, but otherwise it's all free. And I'd like to point out the next webinar that I will do is on October 16th, and it will be about concrete design in RFEM. We'll do a concrete design structure with a little bit more in-depth information. I'll be very happy to have you as a visitor again of this webinar. And before we separate, I would like to thank also Robert Vogel for helping me answering those questions. And I hope to hear or see you again on October 16th for the next webinar. Thank you very much and have a nice day.